Chapter 3, we talked about octet rule, naming anions and cations, how the anions and cations are formed, gaining electrons and losing electrons. And there are two ways to gain octet. One is to form ions, other one is to share electrons to make molecules. So we talk about ionic bond. Now we're going to talk about covalent bond. So that's the topic for today to discuss. Let me go to the last slide. I gone over. Naming ionic compounds. We went over how to name given a formula. You had to identify cation name, cation symbol, sodium plus, calcium plus 2, sodium plus, etc. Like that from the formula. Then get the name of the cation. Then looking at the anion, get the anion formula, nitrate, carbonate, and get the anion name, nitrate. To tell the name of the compound, you combine cation name, then followed by the anion name, calcium, sodium nitrate, calcium carbonate. So we go on over this, how to name. Now I want you to remember one thing here. When you're naming ionic compounds, you don't use prefixes. You don't call diion or if there are more than one ion, you don't call it trinitrate. Right here, tricarbonate. Just call it iron 2 carbonate. So I'm going to talk about ionic compounds, covalent compounds in a minute, and then talk about how we apply octet rule to covalent compounds and how to name covalent compounds. Okay, let's start with this covalent compound. Covalent bond is formed when electrons in the valence shell share electrons with another atom. This normally happens when there are valence electrons between 3 and 7. You cannot lose all more than 3 electrons from to make a cation, or gain more than 3 electrons to form an anion. So only choice is you have to share. Covalent bond is formed by sharing one or more electron pairs between 2 atoms. The pair of electrons shared by both atoms at the same time. They add more electrons, and valence shell can achieve octet by sharing. That's the idea about covalent bond. For example, hydrogen molecule. There are 2 hydrogen atoms, hydrogen gas. If you look at hydrogen gas, the Lewis dot symbol for hydrogen is this, 2 atoms. There are single electron pairs here on each atom. So they share between the hydrogens. This sharing electron gives two pairs of electrons for both atoms. Therefore, it is like helium now. Each hydrogen atom is like helium electronic configuration, noble gas. Therefore, it is stable. Covalent bond formation leads to noble gas configuration. Now, normally sharing takes place between nonmetals and nonmetals. Hydrogen is a nonmetal. Therefore, another nonmetal hydrogen is formed covalent bond. Ionic bond is formed between cation and anions. Metal forms cations, nonmetals form anions. Now let's see how we apply octet rule to covalent compounds. So it's sharing that creates octet. I have written down non-metals here: nitrogen, oxygen, nitrogen, carbon, and hydrogen. All these four are non-metals. Nitrogen, when oxygen combines with nitrogen, covalent bond is formed between oxygen and nitrogen. Any combination. Let's look at the hydrogen and oxygen. Water is formed. How we explain this molecule? This is a covalent compound, non-metal atoms combined together. How we explain is you have to look at the valence shell electrons for each hydrogen atom, two hydrogen atoms, and oxygen atom. Normally, when you bond atoms, the bigger atom is in the middle. Normally, when you build a structure, the bigger object is in the middle. You don't start with small atoms in the middle. So you start with the hydrogen, and this is the middle atom. There are one oxygen, one electron in each. Therefore, they can make a bond between oxygen and hydrogen. Another hydrogen atom combines with remaining electron on hydrogen and oxygen. So these electron pairs are shared now. These are called bonding electron pairs. You draw a line to represent them. That's a bonding electron pair right here, right here. The non-bonding is electron pairs found on the central atom, middle atom, alone. It's a lone pair. So when you describe the bonding in covalent compounds, you draw these structures to show octet is satisfied for oxygen. There are 8 electrons around it. And hydrogen has a duet, just as helium. Oxygen has neon. Therefore, they are stable. So this structure is called Lewis structure. This is a Lewis structure. We normally draw Lewis structures for covalent compounds, molecules. Same idea. When you have nitrogen here, nitrogen with hydrogen, it forms ammonia, NH3. Same idea. you have the central atom, big atom, with 3 single electrons, hydrogen with 1 electron each. They could be paired up with these 3 in the nitrogen atom. Therefore, 4 bonding electrons are shown by lines. Sometimes we write this structure also. The lone pair also shown by a line here. So that's how you get the Lewis structure. There's 8 electrons around nitrogen, 2 from each, 1, 2, 2 plus 6 is 8, octet is 4. Ammonia has 3 bonding pairs of electron, bond pairs, 3 bond pairs, 1 lone pair. Oxygen has 2 lone pairs, unmoded. Methane, which is called natural gas, carbon makes 4 bonds. There are, in the Lewis dot structure of carbon, there are 4 single electrons. Each can combine with 4 hydrogen atoms with 1 lone pair, single pair, form 4 bonding electrons. So in methane Lewis structure, this is called Lewis structure of the molecule. These are Lewis structures. Show bonding electron pairs, non-bonding or lone pairs. These are all valence electrons. We're going to talk about this, how to add up valence electron, get the number of valence electron in the molecule. So that's how we describe bonding of nonmetals to nonmetals sharing electrons. Hydrogen get duet, 2 electrons. Others got 8 or octet. Now, to draw a Lewis structure, you have to get total number of valence electron in the molecule. Total number of valence electron in the molecule means you add up the valence electron in each atom of the molecule. For example, water has 2 here plus 6 here is 8 valence electron. Now, after you counted the 8 valence, the Lewis structure should have 8 valence electrons after you draw it. Connectivity is important. What do you mean by connectivity? The middle atom is selected. Oxygen is big atom. So you connect middle atom to the, you got the idea. Hydrogen here, oxygen here, hydrogen here. That's the connectivity. Middle atom is always a big atom. In the periodic table, you can see oxygen is bigger than hydrogen. Connect the single, connected is middle is oxygen, you connect with that's this step. Then Lewis structures show bonding electrons. There are 2 bonding electrons. And you have to show non-bonding also here. So in the Lewis structure, sometimes we write dots. Or we write lines. So some molecules, to fill the octet, you need to form more than 1 bonding electron pair between two atoms. For example, single bond is a 1 electron shared between two atoms. Double bond is a 2 electrons shared between two atoms. For example, carbon dioxide. Carbon dioxide has double bond between. I draw the picture here. Here, single bond, 1 electron pair, 2 electron pair, 3 electron pair. 3 bonding electron pairs shared between two atoms is a triple bond. Okay. You guys have any questions? All right, that's how you describe Lewis structure of a covalent bonding. Now we're going to draw some more structures. Hydrogen peroxide. Hydrogen peroxide is this molecule with 2 hydrogen and 1 or 2 oxygen. Methanol is an alcohol. Alcohols have OH groups. This is a carboxylic acid, acetic acid. So connectivity has to be determined. We're going to look into that, how to draw Lewis structures for them. Normally the formula is given. Sometimes connectivity is shown here. This is C. Carboxylic acid bond like that. Oh, I'm sorry, this is this. The alcohol is, this is this. So let's look at each one individually. In hydrogen peroxide, there are 2 hydrogens, therefore 2 times 1. Valence electrons is 1, valence electrons 1, 6 on the hydrogen, oxygen. 2 times 6, you add them up. 1 times 2, 2 times 6, you get 14 total. There are going to be 7 pairs. So now we get the connectivity. What is the connectivity? Connectivity is oxygen should be in the middle because oxygens are bigger than hydrogen. So I wrote down that that's the connectivity. Then there are 7 electron pairs. You have to put octet to oxygen, duet to hydrogen. So in this structure, there are 7 electron pairs or 14 electrons. 1 pair, 2 pair, 3 pair, 4 pair, 5, 6, 7. So number of valence electron pairs or valence electrons should be shown on the Lewis structure. It also shows oxygen has an octet, both oxygen. Hydrogen has a duet. So there's a stable molecule, hydrogen peroxide, because all atoms have noble gas configuration. So this is the Lewis structure of hydrogen peroxide. Now this has, carbon has 4 valence electrons, hydrogen has 1, oxygen has 6. I'm going to the periodic table and see how many electrons are in the valence shell, the outermost shell. When you add 4 plus 3 times 1, 1 times 3 is, this is carbon, this is hydrogen, this is oxygen, this is hydrogen. So you get 14. 14 divided by 2 is 7, just like that one. So connectivity is that this is O. So after you got the connectivity, you put the hydrogen, 3 hydrogen on the CH3 and fill up the octet for each atom. So when you do that, you get this picture right here. So you put the lone pairs on oxygen. Now it has 8. So therefore, Lewis structure has 7 electron pairs. You count all these 1, 2, 3, 4, 5, 6, 7. 7 electron pairs. Octet and duet to each hydrogen. Duet octet is on the oxygen atom. That's how you draw Lewis structures. Did you get the idea? You count the valence electrons, get number of pairs, connectivity is decided, then you add small molecules to the middle big atoms, which we select to start the connectivity, then complete the Lewis structure. Same number of valence electrons you start with should be in the Lewis structure. Now, this is the acetic acid. There are, I'm not going to count all these, it's 12 electron pairs. This comes from 4, 1, 4, 6, 6, 1. That 6, 6, 1 is for oxygen. The 4 is for the carbon, hydrogen, carbon, 2 oxygens, and 1 hydrogen. That's how you got the valence electron added. Connectivity is this. This is a connectivity. So you add the hydrogens to carbon and hydrogen to OH. Then after that, you fill up 2 more electron pairs to here. That's what you got. There are 12 electron pairs. I'm not going to count. There are 12 in the molecule. So what you started was 12 electron pairs. You have 12 electron pairs, including bonding electron pairs and non-bonding electron pairs. So you get the idea about now how you describe the octet rule using Lewis structures in forming covalent molecules or covalent bonds. Now we're going to look into detail. Water. There are octet 8 electrons. 2 from here, 6 from here, added up to 8. So this is water Lewis structure. Ammonia is also 8. 5 valence electron. 5 plus 3 is 8. That's how you get it. So carbon has 4, hydrogen has, each hydrogen is 8 also. Methane molecule. This is the Lewis structure of water, ammonia. If I ask you what is the Lewis structure of ammonia, you should pick that one in the middle. That's the ammonia. Each molecule have different Lewis structures. HCl is a non-metal. Hydrogen is non-metal. It's also covalent molecules is 8 electrons. 7 from here, 1 from here. 1 from hydrogen, 7 valence electrons. So in this compound, if you look at, you have 8 from 4 from hydrogen, 8 from 2 times 4 is 8, 12 electrons divided by 6 to get 6. Now, if you look at this, there are 1, 2, 3, 4, 5, 6. There are 2 electron pairs. So therefore, there's a double bond in the molecule. All the electrons should be put in. So to get the octet between 2 carbons in ethylene, you should have double bond between carbon. Acetylene, same here. There's 5 electron pairs. 1 here, 3 here, 1 here, added up. There are 3 lines in the middle, that's triple bond. Adds up to 10. 5 times 2 is 10. Sometimes we count the pairs. Sometimes if you count the pairs, you have to divide it by 2. If your electrons, pairs multiplied by 2. Formaldehyde. Lewis structure is this. Connectivity is carbon, oxygen, you put the hydrogen. Then 12 electrons in the Lewis structure, or 6. 1, 2, 3, 4, 5, 6. 6 electron pairs. So it's pretty, this is carbonic acid. When you dissolve carbon dioxide in water, you get carbonic acid. It's in your soda drink, carbonated drinks. This has 12 electron pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if somebody asks you how many double bonds in the molecule, there are 1 double bond right here. How many lone pairs? 6. There are 6 lone pairs. So these are the questions we ask. How many bonding electron pairs? How many carbon-oxygen bonds? There are 2 here. Carbon-oxygen single bonds, 2. Carbon-oxygen double bond, 1. Now there's a exception to the octet rule. This is because period 2 has only 2s and 2p. Therefore, they can have 2 electrons here, 6 electrons here. We talked about this. 8 electrons, octet. For the period 2, it's a lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. These elements always have 8 electrons. There's no exception. It obeys the octet rule. They have maximum of 8 electrons. But period 3, third period, starting with sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. They have 3p electrons and 3d also. There could be more than 8 electrons. Here is maximum is 8. Therefore, certain periods, except the second period always obeys octet rule. Third period, fourth period, elements have more than 8 electrons because of the d orbitals. Atom can have more than 8 electrons, more than. So therefore, it is an exception. Lewis didn't know around that time. This is because electronic structure tells us third periods and higher periods can have more than 8 electrons in the shell. For example, this is phosphorus, third period. This is 8 electrons. That's okay. That's not an exception. But if you look at this phosphorus atom, there are 10 electrons, 5 electron pairs. Therefore, this is kind of an exception. If you look at the other one, phosphoric acid. Phosphoric acid, we're going to look at. This is H3PO4. You're going to see this as acid. So this has 10 electrons. Therefore, it's an exception to Lewis structure. So we ask question. I will show you the structure, then you look in the middle atom and find out where they have more than octet. This is okay. This is 8. So there are sulfur compound. This is okay also. That's 8. But this one has 10. This is exception. Sulfuric acid, H2SO4. You're going to hear about these compounds. Has a sulfur atom in the middle. It has 12 electrons. Therefore, exception. So even though we say octet rule is followed mainly for second period, sometimes other period also, but there are examples when the d orbitals are filled. The shell could have more than octet. Now we talked about bonding in covalent compounds, covalent bonding. We talked about Lewis structures. There are exceptions. Valence, how the octet is, or sometimes exceptions are formed. Covalent bond is a compound in which all bonds are covalent. All non-metal form covalent bonds. Let's look at how we name binary compounds. Binary is 2 elements, MX. Let's see, XY. X is the one element, other one is this could be carbon oxide. It could be carbon monoxide, carbon dioxide. So the less electronegative, carbon has less electronegative. We talked about the electronegativities in the previous class. This has less electronegativity. Carbon electronegativity. You write down the less electronegative carbon. Then the second element is oxide. Oxygen converted to oxide, just like in naming covalent compounds. But you normally use prefixes to tell number of atoms. Carbon monoxide, carbon dioxide. Di means 2 oxide. So we're going to show this in a minute. Prefixes di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, 7, Mono is 1. So you tell the subscript of each atom, dioxide, trioxide, etc., tetraoxide. Nitrogen oxide is the name. We don't call nitrogen monoxide, just nitrogen oxide. This molecule is sulfur. There are 2 fluorines, difluoride. The second element, sulfur, is less electronegative. Fluorine has the highest electronegativity. Therefore, sulfur difluoride. For example, this molecule is nitrogen is less electronegative, nitrogen, than oxygen. You call it nitrogen dioxide. I for the second element, suffix. Suffix is something you add to the beginning of a word, suffix. Prefix is to change the oxygen to oxide. This is prefix. Id is suffix. Prefixes are used to tell number of atoms.
Use your fingerprints to unlock the device.
Aspect of Lewis structures. Lewis structures are normally only one Lewis structure describe a molecule, bonding in a molecule. And also properties also described by the Lewis structure. How many double bonds, single bonds, and things like that, bond distances. But there are cases where one Lewis structure is not adequately describe the real properties of the molecule, bond distances mainly. For many molecules and ions with double bonds, this happens. For example, I'm going to give the examples. In this molecule, no single Lewis structure can provide accurate representation. Therefore, 2 or more, 3 is really common Lewis structures. But carbonate ion has 3. That's why we wrote 3. I shouldn't have said 3 here. So carbonate ion is this. When you write the Lewis structure of carbonate atom, 2 minus. Carbonate is CO3 2 minus. There are 4, 3 times 6 plus 2. There are negative charge. Therefore, this adds up to 24 electrons divided by 12. 2 is 12. If you look at this, has already 4 here, 5, 6, 7, 8, 9, 10, 11, 24 electrons. Is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 electron pairs. But this one is problematic. In the real carbon, only one place. All the bonds are shorter than single bonds. Double bond is shorter than single bond. Little shorter, all the bonds. Therefore, to represent why these all 3 are equal length in the real carbonate molecule, you have to show structure this double bond could be at different places. You can move electrons. I didn't move it right. You can move this electron to double bond here, and you get this structure. You can move this electron here, move this back there, and you get this structure. Carbonate ion is really accurately described by 3 Lewis structures. When the molecule needs more than 1 Lewis structure to describe the bonding, so that's called resonance Lewis structure. These are called resonance hybrid. Now you had a mixture of all these. This idea came about 1930s. Linus Pauling, who discovered the electronegativity, also found out about resonance. Many molecules and ions are best described by writing 2 or more Lewis structures. Individual Lewis structures are called contributing. There are 3 for carbonate ion. Double-headed arrow. Remember, I moved the electrons around between individual atoms to produce contributing structures. Double-sided arrow, double-headed arrow is used to show the resonance. The molecule or ion is a resonance hybrid of various contributing structure. Hybrid is a horse and a mule produce a donkey. Donkey is neither horse or mule. So it has both, it's a resonance hybrid of, so to speak. So real properties described by both, mixture of both. The curved arrows are used to generate contributing structures, one to the another. The tail of the arrow identifies the pair of electrons. Let's look at that. See, if you want to move this electron pair and move down here, you move the electron pair and curved arrow will move and you will get negative charge here. And negative charge is here. So I am not drawing it there. From the bond, you can move bonds to adjacent atoms. You don't change the position of the atoms, only the valence electrons. Let's look at this one, sulfur trioxide, also example of Lewis structure with resonance. So this curve arrow moves this negative charge. Here now. There's no negative charge here. Somehow there are 3 electron pairs here. Double bond is now in here. This is second double bond. That's the third double bond. 3 different places. These 3 bonds in the sulfur trioxide are equal. So therefore, resonance structures describe their properties. Now, there are conditions for drawing resonance structures. All contribution structure, there are 3 for the sulfur trioxide, have the same number of valence electrons. We didn't change the valence electron. Obey the rules of covalent bonding, octet rule. No more than 2 electrons in hydrogen and 8 electrons in the second period element. Remember, second period is the only one that obeys completely octet rule. Third period elements can have up to more than 8, 10 or 12 because of the 3D orbitals. Differ only in distribution of valence electron. The position of all nuclei must be the same. You don't change. So this is how we describe the Lewis structures of certain double bonded compounds. Have same number of paired and unpaired electrons. Okay, I'm going to change the topic now. We describe Lewis structures. We draw Lewis structures. We pick the connectivity. We fill in the octet or duet to the hydrogens and other elements octet. So we talked about resonance. Certain Lewis structures require drawing more than one Lewis structure when they have double bonds that could be distributed within the molecule in different places. Now, Lewis structures never tell the shape of the molecule, molecular shape. It only tells bonding, whether it's an octet or duet. And single bonds, bonding electron pairs, lone pairs, they talk about bonding aspects, not about the shape. So this idea, in the Lewis structure, there are valence electron pairs. Repulsion of them could lead to prediction of molecular shape. So this idea was developed after Lewis. So this is an important idea to predict the shape of a molecule, covalent molecule. Valence electrons on an atom may be involved in forming single, double, triple. We name normally single bond is here, double bond is here, triple bond is like that, 3 lines. Or it could be unshared, just no bond, but lone pairs. So in an atom, you could have lone pairs, single bond, double bond, triple bond. They all form a group of electrons. There are more electrons in the single, double little more, triple more. If you compare the lone pairs, there are 4 things, the single, double in an atom, single, double bond, triple bond, and lone pair. So when they are found in an atom, they are negatively charged. They are negatively charged around the atom. For example, oxygen in water, there are 2 lone pairs. 2 lone pairs here, bonding electron pairs, these 2. Therefore, there are 2 lone pairs, 2 bonding electron pairs. total of 4 pairs. We count all of them, double bond, single bond, it's just as an electron group, electron collection. 4 electron pairs in the oxygen atom. When you put 4 electron pairs, they repel from each other. So they arrange in a tetrahedron. Tetrahedron, I didn't write it correctly. Because like charges repel each other between these lone pairs, bonding pairs, triple bond, double bond, they tend to be as far away as possible from each other. So let's look at example. Lone pairs, bond pairs, double bonds, single bonds. There are 4 groups. Will decide the shape. For example, methane. What is the shape? Based on valence shell electron pair. There are 4 bonding electron pairs. Bonding electron pairs. This is here. When they distribute away from each other, they form a tetrahedron. This angle is 109 between each carbon-hydrogen bond, 109. So this is a tetrahedral shape for methane molecule. That's how you explain shape of a molecule, methane molecule, using Lewis structure. Look at this central atom. To predict the shape, central atom is the one that decides the shape. The Lewis structure shows carbon surrounded by 4 regions of electron density. These are this is the electron regions. In this case, bonding electron pairs. They repel each other. They form tetrahedron. According to valence shell electron pair repulsion theory, the 4 regions radiate from carbon at an angle of 109.5, tetrahedral angle. The electron put pair geometries. The geometry is tetrahedron. When you don't have lone pair of electrons, it's a bonding electron pairs. Lone electron pairs. The shape is the same. If you have we're going to talk about lone pairs, how we change the shape of the molecule. Tetrahedral molecule with 4 bonding electron pairs is tetrahedral. Ammonia. We talked about this Lewis structure. There's a lone electron pair, lone pair of electron, bonding electron pairs. How many of them? 3, 1. There are 4 groups here. That's a bonding electron pair. This is the lone pair. That's how they distribute. So this lone pair or unshared electron pair pushes the single bond has longer than electron is kind of concentrated towards the middle atom. Therefore, this pair repels this bonding electron pairs more than in a methane molecule. Therefore, this 109 tetrahedral angle is changed to between these to 107. So therefore, we call this molecule not tetrahedral. We don't look at, when you tell the shape, you don't see the electron. You see only the atom. 3 atoms. That's the shape. This shape is a pyramid. So molecular shape is decided by atoms, how we see atoms. So this idea, even though all the electrons are distributed in a tetrahedron, we don't see the lone pair, unshared electron. Therefore, molecular shape is pyramidal or trigonal pyramid. The base is triangle here. There could be a square pyramid where the base is 4. This is base is 3, trigonal. Trigonal means triangular. Ammonia molecule, what's the shape? Pyramidal or trigonal pyramid. The molecular shape of water, same idea. There are 2 lone pairs of electrons, 2 bonding electron pairs. This is the lone pairs. This is the bonding electron pairs. You don't see them. When you see the atoms, you only see 3 atoms distributed in a bent. Water molecule is like this. There are two lone pairs. We don't see them. So we don't write them down. So shape is bent. Bent is the angular. Sometimes we call it angular. Water molecule shape is angular. Ammonia molecule pyramidal or trigonal pyramid. Methane molecule is tetrahedral. That's how you predict the shape of the molecules. All right. Now there's a, why it's 104. There are, in ammonia, you had only 1 lone pair. There are 2 lone pairs. Therefore, these 2 pushes further reduce the angle 109 to 104. The water molecule has angle about 104. That's how you describe from the Lewis structure the shape of the molecule. Angular, angle is 104. So you can have this molecule, formaldehyde. There are 3 groups here. 1 double bond, 2 single bonds. But when you have 3 pairs distributed, it's a triangle plane. It's like this. It's in a planar molecule. This is called trigonal planar molecule. This formaldehyde has 3 electron pairs. 3 electron pair distribute equally in space, produce 120. This is little less than 120. Because this double bond electron pair is little stronger. They have more electrons. They pushes them further. Therefore, this angle is increased from 120 to 121. Those 2 get squeezed into 160. So side view, this formaldehyde molecule is trigonal planar, like trigonal bipyramid, trigonal pyramid for ammonia, trigonal planar. This is also trigonal planar. So this is planar. When it other one bonded is planar. This is whole molecule is a flat molecule. This is planar molecule. Now, how many of you getting this? The idea. The acetylene molecule, there are carbon atom with is 180 linear. This is linear. This is also, this carbon also linear. So 180 here, 180 here, here to here. Therefore, it's a linear molecule. So acetylene molecule is linear. So that's how you predict shapes of the molecules from valence shell electron pair repulsion theory, starting from the Lewis structure. This is Lewis structure. We start from there, look at the number of electron pairs, then describe the bonding, molecular shape. In acetylene, it's 180, linear is 180. Now we're going to stop at this point. I'm going to talk about polarity of covalent molecules in next class period. Can you sign up the chat box? Okay, I'm going to stop. Anybody there?
Oh.
All right.